And then let's look at our asymptote again. Okay, question came up on campus. Okay, how could you get this? Let's talk about what the y-intercept does. What's the y-intercept do? Okay, good job. When you plug in 0, it's the value you get out. When you plug in 0, it's the value you get out. So let's take our original equation, plug that in. So y equals negative e to the 0 plus 2. That gives us y is equal to negative e to the second power. Plug that in our calculator. That's it. Got the negative 7.38. Other questions on that? Okay, Cornerstone instructors, if you want to work another example, this would be a good time to pause and work through it. On campus, do we want to work another one? Okay, let's keep on a trucking then. Let's go back. Okay. Now we talk about a concept that really in this section just comes up because of an application that E has, but we talk about the difference between an average rate of change and an instantaneous rate of change. Now, surprisingly, every one of you knows what this is, even though you probably have never heard the word associated for it. So let's put you in a situation real quick. You got a hot date tonight. You get in the car, you borrow the car from your parents, because remember, you just got that brand new Ford Mustang from that penny scheme you ran with your parents. So you got your brand new Ford Mustang, you get in it, your date's at 8 o'clock, and it's 8:02. And her house is 5 miles away. So you get in the car, you floor it. Driving down the highway by your house, fortunately there's the sheriff right there. You see the sheriff, you slam on your brakes. Sheriff comes up, of course, puts the lights on, he pulls you over. He says, hey, it's a 60-mile-an-hour road, you're going 85. He says, how'd you get that? When I saw you to when I stopped, if you look at how fast I was going over that interval, I was only going 12 miles an hour. And if you take the time that you've had me pulled over to here, my speed over that interval from when I saw you to right now was about 1 mile an hour. I shouldn't get a speeding ticket. I should get one of those tickets where I get to go out to dinner on the police department for good driving. He said, I don't care how fast you were going over the last 10 minutes. I care how fast you were going at that moment I saw you. I hit you with the radar, 85 miles an hour is how fast you were going. Well, that looks at the impact of the two things we're going to talk about today. Instantaneous rate of change is how fast you're going at a point. Not over the last 5 seconds, over the last 0.5 seconds, over the last 0.05 seconds, but just at that one instantaneous point. Average rate of change is how far you've been going over an interval, over an amount of time, like the last 2 hours, the last two seconds. So the two things we're going to talk about today, average rate of change, instantaneous rate of change. Average is over an interval or over some amount of time. Instantaneous is just at a point. So that's like when that cop hits you with the radar. Right at that moment, that's the instantaneous rate of change, how fast you're going right at that point. Now, remembering back even from Algebra 1, we do have an equation for rate of change. Change in our output value over the change in our input value. For many of the applications that we're going to talk about today, it's the change in our output over the change in time, or how long it took for that change to occur. So again, average rate of change is over an interval. Instantaneous rate of change is over a point. So let's take a look at an example. The example actually with e to the x is why we talk about this. So we have a certain bacteria, I can't pronounce that, but maybe your teacher can, grows at a rate of y equals e to the x, with x being seconds since infection, and y being the number of bacteria in the host. Notice at time 0, how many bacteria are in the host? Okay, don't say I don't know. Plug in 0 for x. E to the 0 is equal to what? Yeah, anything to the 0 power is equal to what? 1. So just at that instant of infection, times 0, there's 1 bacteria. We're asked to find for this one, find the average rate of change over the first 5 seconds of infection, and then find the instantaneous rate of change at exactly 5 seconds, which we're going to have to come up with the scheme to approximate for. So really quick, I would like you to find the average rate of change over the first 5 seconds of infection. And can I pause for just a second? I got to get a drink. Sorry. Can you pronounce that bacteria?
I like methyl.
Okay, I'm ready to start.
It's an Italian strain.
It's a very, very infectious. Not this time of year, but... Okay, Frank, I'm ready to go again. Okay, so we want to find the average rate of change over the first 5 seconds. So let's go back to the DocCam. We need to find out how many bacteria we acquired over the first 5 seconds. So again, our function y is equal to e to the x, which just for convenience sake, I'm going to change to f of x. So I need to find out how many there were at 0 and how many there were at 5. And for the purposes of this problem, I'm going to round to the whole number. E to the 0, we found out earlier, that's equal to 1. Let me flip over the calculator and plug this in. And e to the 5th. Oops, gotta plug in e. To the 5th. Which gives me approximately 148. Let's flip back to the DocCam there. Let's flip back to the DocCam on campus. So our average rate of change is equal to the number of bacteria we had at 5 seconds minus the number of bacteria at 0 over 5 minus 0. That's our interval, that's how long it took. We found that f of 5 was 148. F of 0 was 1 over 5 minus 0. 147 over 5. Which is approximately, nope, exactly 29.4 bacteria per second. Okay, let's stop and check up just real quick. That's our average rate of change. So in other words, over the first 5 seconds since infection, the bacteria are growing at a rate on average of 29.4 bacteria per second. That's kind of like for the cop analogy, for the first 5 seconds since you left your house, that would be the analogy to the speed that you're going over the first 5 seconds. Why would that not be a good approximation of exactly what's happening at 5 seconds? Okay, good answer. Okay, it's because at the first second of infection, there's fewer bacteria, so they're growing at a much slower rate than they were farther along in this section or farther along with the bacteria. So that's not a real good approximation of what's happening at 5. So we have to look closer at what's happening at exactly 5 seconds. So what we want to do is take a look at that formula, our change in y over our change in x, and I want to make that change in x as small as possible. So I don't want it to be like 1 second. I want it to be like 0.1 or 0.01 or 0.001 or 0.000001. Let's talk about how we do that. Let's set up our equation and set up our formula. So our change in y over our change in x so we want to find a point very close to 5. So we want to be very, very close to 5. So I'm going to call the difference between our point and 5, I'm going to call that h. So the difference between 5 and our second time rate. So to find our rate of change, we're going to have f of 5 plus h minus f of 5 over 5 plus h minus 5. Now, you might be saying, okay, this is a conceptual idea. Let's see if we can apply some math to it first to see what's happening here. So let's take a look at, first the denominator. 5 plus h minus 5 means we have h on the bottom. And on top, we would have e to the 5 plus h minus e to the 5. I think there's any way we can simplify the top. Okay, For this one, let's go to the calculator. Let's plug this in and see what we can do to approximate that. So again, what does h represent? Okay, h is the distance between our first reading, our second reading, or how far our interval is. We want to make that as small as possible. Fortunately, we can't put h into the calculator. We got to put x. So let's go to our first. Let's plug in. I'm probably going to want to put some parentheses around it. E to the 5 plus x. Minus e to the 5 divided by x. Oops, and where I want to put x. E to the 5. There we go. And let's take a look. So again, x is going to represent our time. Why does it give us an error at 0? Because 0 is the optimal answer. If you have 0 seconds between your readings, there's 0 seconds between that. That's what we want, isn't it? Let's go back to our original equation. Let's take a look. Why would 0 give us an error? And yep, that's because we're going to end up with 0 in the denominator. That's the paradigm or the quandary of the first 2 chapters of calculus. So I'll leave that to 172's instruction. Let's take a look. Let's make that closer though. What's our change, or what's our interval? And let's go back to the table. What's our change, or what's our interval on this one? Just thinking about it, There we go. Our interval is 1. Let's change it. Let's make it a little bit smaller. So let's make that instead of 1. What do you think we should make it? Okay, let's start at 0, and let's go up by 0.1. Now let's look at our table, see what's happening. Okay. Notice again at 0 it's giving us an error, but as that interval closes down, or as that interval gets smaller, what does it look like it's approaching? Okay, about 156. Let's make it even smaller. Let's make it 0.01. So in other words, for the cop, instead of being 0.1 seconds, let's go 0.01 seconds. See if we can get a better approximation. Okay, now as we get closer, we're seeing it's going to 149. Let's make it 0.001. Okay, now we could continue this for on and on and on, but as we see with this one, where is it approaching as we get closer to 0? 148.5, 148.49. That's what we're looking for. What value does it approach as that interval, or as those 2 times get closer and closer to 0? Let's flip back to the document camera real quick. So what's our best guess for that approximate rate of change at that point? It'd be 148.49. Now, if you wanted to, if your life depended, again, you're trying to get those 23 consecutive A homework assignments so you can get that Ford Mustang, you could keep going to 0.000001. You could keep putting zeros in there until your calculator runs out of room. Notice, though, this is pretty darn close to what number? Let's go back. What was e to the 5th? Yeah, 148. And what's our rate of change at this point? Approximately 148.49. Yeah, that's probably more than a coincidence. But that's an exploration for calculus. So again, to refresh today, what we talked about, we introduced what E was. We talked about the translations of the graph with E, and then we worked through one bacterial problem with using E to the X to find the average rate of change, the instantaneous rate of change at a point, which probably there's a connection between what E to the X is and what the instantaneous rate of change is at E to the X, but that's a fascination for later. Again, thanks for joining us today. Those of you on campus, we'll stop real quick and we'll give you your homework before you take off today. Thanks.